Now today we're going to solve an advanced question of circles plus limit. The question is, let capital S1 and S2 be two circles of unit radii touching each other externally, and the line L is one of the directed common tangent, that is commonly known as DCT. Now a circle C1 with the radius small r1 is such that it touches the two circles capital S1 and S2 and the line L, that is DCT. Similarly, few more circles are there starting with C1 to Cn are the circles corresponding the radii are small r1, r2, r3 and so on till r of n. Now, where a particular circle C of r touches the circles S1, the starting one, and the previous one to this one, C of r minus 1. And it is given that C of n is one of the directed common tangent between them. So we have to calculate this limit n is tending towards infinity. The reciprocal sum of radius is given upon n cube is given. So we have to calculate this value. So let's start. Now this question has many parts, so I'm going to tackle them one by one. So first thing I'm going to start with the length of DCT. So let's say this is the first circle. Let's call this as capital S1. And let's say one more circle, which is S2, which is touching these two circles externally, as you can see here. Let's say one more line is which is tangent to both of them is called as direct common tangent, commonly known as DCT. Now I'm going to derive and result the length of DCT between any two circles which are touching externally. And I'm not doing for equal radii. As you can see, these two circles are not of equal radii. One is slightly smaller than this other one. So let's say the center line joining center 1 and center 2 is this line. Now from this centers, I'm going to drop perpendicular on the DCT. So let's say from C1, if I'm drop a perpendicular on the DCT, let's call this point of tangency as D. Now from C2 as well as I'm going to drop a perpendicular. Let's call this point as C. Now our objective is the length of DCT here. So length of DCT is, I think it is equal to DC here. We'll be calculating DC in the terms of radii of the circles. So I think the first radii is R1 as you can see here, and the second radii is capital R2. Again, I'm deriving for unequal radii. Here it's R1 and R2 are given 1, so I'm going to derive later on for R1 and R2. Now, from center 2, I'm going to drop a perpendicular on line joining C1 and D. So as you can see, this is the perpendicular and 90 here. Now, our objective is to calculate the DC. So can I say DC in this? It is 90, 90, 90 everywhere. So I think it's a rectangle. And if I denote this point, let's say P point. So I think it is equal to DC is equal to PC2 here. And in this triangle, in triangle PC1, C2, in right angle triangle, I think we can calculate the distance PC2 easily because the distance between the line joining the centers, I think that will be equal to R1 plus R2. Now I think I can write this as root over R1 plus R2 whole square. This is hypotenuse minus, I think base we can determine here. So this length here, which I'm denoting, can be written as difference of radii only because I've dropped perpendicular from C2 on C1D. So I think this distance is R1 minus R2. So square of this I'm going to subtract from here and root over closed. So from here we can calculate the DC. DC value will be root over, as you can see, plus R1 square minus R1 square will cancel out, plus R2 square minus R2 square will cancel out. We'll get 2 minus or minus plus 2, that is 4 R1 R2 root over. So from here DC I can generalize, that will be equal to twice and root over R1 R2. And again this will be valid for any two circles of unequal radii, as you can see. Now we can calculate, we can go to the next part of the question. Now moving on to the next part of the problem, let's try to understand the setup here. So the question says that C1 is a circle which is touching the two circle. Let's call this as S1 and S2. So let's say the circles are S1 and S2 which are touching each other externally already. Now C1 is fitting in such a way that it is touching the S1 externally as well as S2 externally, and there is a common DCT which is passing through both of them, as you can see. Now the reason being I kept this as R1 and R2, clearly in the question it's given that the two circles S1 and S2 are unit radii. Now my objective is to keeping them as R1 and R2 is because I want to derive a general result, the distance between the circles which are coming next on. Okay, so let's say the point of contact with the first circle is P here of the tangent. Let's say this is R and this is Q here. Now, can I say that PQ here distance will be equal to PR plus RQ? And in the last slide, we have learned if two circles of unequal radii are touching each other externally, so the length of direct common tangent will be, as you can see, 2 root over. Now, we haven't denoted the radius of this C1 circle. It's given as small r1 in the question. So it will be equal to capital R1 and R2, as you can see here, because it is between S1 and S2, PQ. Now, PR will be between S1 and C1. So I'm going to write this as 2 times root over capital R1 and small r1, plus this will be 2 times root over, as you can see here, capital R2 and small r1. Now here 2 will cancel out. Now throughout the equation, what I'm going to do here is I'm going to divide by a number, that is 1 by root over R1 capital R2. Now here our objective is, using this setup, we have to find the value of small r1 in the terms of capital R1 and R2. So this is our full objective here. That's why I'm dividing by, throughout I'm dividing by root over R1, R2, small r1. The moment you divide, you will get 1 upon root over R1 is equal to 1 upon root over R1 capital R1 plus 1 upon root over capital R2. Now I got a general result which is valid for any radius with this setup. Now let's focus on R1 here. So if I want to calculate R1 here, as you can see, capital R1 and capital R2 are given unit radii circle. I'm going to substitute capital R1 and R2 as 1 and 1. So we'll get 1 upon root over R1 as 1 plus 1. And from here, I can say R1 is 1 by 2 square, easily you can say. Now let's do the calculation for R2 here. Now for R2, there is a circle C2, which is inscribed in such a way that it touches, as you can see, the circle 2 touches C of R minus 1, that is C1, and S1, it's clearly given in the question. So that means one more circle is there which is inscribed in such a way that it is touching, this is C2, it is touching C1 as well as S, as you can see here. Now, the C2 is fitting in between C1 and S, you can see. So I can apply the same result using this. The one which is smaller here will come here. I can generalize this result. So 1 upon root over R2 can be given as 1 upon root over, as you can see, capital R1 plus 1 upon root over small r1. So here I can write this value as 1 by root over R2 is, this is 1 plus 1 by root over R1 we have derived just now, that is equal to, I think, 2 here. So from here I can say R2 is equal to 1 by 3 square. Now if you notice, the next thing is, if I draw C4 or C3 here, C3, C4, again and again and again and again, I have to calculate in the same way. The way in which I have calculated earlier, like PQ is equal to PR plus RQ. Again, I have to join the direct common tangents, and the same way I'll be calculating. But I think we can generalize the result here. So R of n, I can write clearly here, R of n will be 1 more square. So n plus 1 whole square here. So this will be the general result I'll be using to get the limit value. Now let's moving on to the next slide. Now we have generalized the formula of R of n in the terms of n. I'm going to plug all the values of R of n in the limit. So here we'll get this as limit n is tending towards infinity. Since R1 is 1 by 2 square, so 1 by R1 is 2 square here. Similarly, R2, 1 by R2 is 3 square, 4 square, and so on till last term will be n plus 1 whole square. Now whole thing is divided by n cube here. Now in order to make the summation of n square perfect, I'm going to add 1 square and subtract 1 square here. Now I think this looks like summation of n square. And summation of n square, you know, that is n into n plus 1 multiplied by 2n plus 1 whole thing divided by 6. Now instead of giving you summation of n square, they have given n plus 1 square. So wherever you see n, I'm going to replace n by n plus 1 here. So here we'll get limit n is tending towards infinity. Here we'll get this as n plus 1 multiplied by n plus 1 plus 1 multiplied by 2 into n plus 1 plus 1 and then divided by 6 here, minus 1 whole divided by, as you can see here, n cube. Now if you check here, the highest degree which you are getting of n is in numerator is 3 and denominator highest degree is 3. Since the form is infinity by infinity, the answer will be coefficient. Coefficient of n cube will be our answer. So if you check the coefficient of n cube in numerator, that is 1 by 3, in denominator it's 1. So our final answer will be 1 by 3. The value of the limit will be 1 by 3. This will be our final answer, and that will be all.